This is going to be 33-1. We're going to take a look at concavity and the second derivative test. So we're first going to start with this concept of concavity. Now, the definition says let your function be differentiable on an open interval, and we're going to say that that open interval is I. The graph of f is concave upward if on that interval the derivative is increasing on that interval. So it's kind of like if we look at the change in slope on that interval and that's increasing, we're going to say it's concave upward, and it's concave downward if the change is decreasing on that interval. So if the derivative of self is decreasing on that interval. Now, the way that we test for it is we use the second derivative. So you take your function, you find the derivative, that's your first derivative, you find the derivative again, that's your second derivative. And so if your derivative is greater than 0, so the values on the interval is greater than 0 or positive, then you can say that it's going to be concave upward. And if on that interval your second derivative is less than 0, then we're going to say that it's concave downward. Now this is kind of visually what it kind of looks like here. So if we notice this graph here, on this interval it's going to be concave upward. And the reason is because the change in the slope is increasing. Now it's kind of weird, you're probably thinking to yourself, well, the slope is decreasing. Well, we're not looking at the slope itself, we're looking at the change in the slope. And so, if we draw all these tangent lines, as we go through here, if you notice, all of those tangent lines are creating me an increasing slope. So it goes from decreasing till it gets to about here, and then it's even increasing, but the entire time my slope is increasing. And likewise, the change in slope here is decreasing. So it starts from increasing, and as I draw all these tangent lines, the tangent lines keep getting smaller and smaller and smaller in terms of my slope being decreasing and decreasing more and more. So let's look at a brief example here. It says the graph of f is given below. Determine graphically the interval on which my function is concave up. And so it seems like it could be off just a little bit, but it seems like it's concave up between here and here. And so I can say concave up is going to be between, what is that? The interval 1.6. Maybe it's even more towards here. See, it's decreasing, and then yeah, it starts getting larger there. So maybe even 1.8 all the way to, and it's increasing, and then it starts decreasing, I don't know, somewhere around here. So maybe like let me erase that so we can look. Maybe like 3.3, 3.5, 3.4, like 3.3, somewhere around there. I mean, it's a rough estimate just by visually looking at it. But the part B where it's concave up and decreasing, well, it's only decreasing. So we said that about right here is when it's starting to be concave upward. And then from here all the way to here is where it's going to be decreasing. So the decreasing part would be the 1.8 all the way, and it looks like that's like 2.5 approximately, right? It's not like ultra accurate, but it's kind of like an approximate from what we're looking at. And just in case you're wondering, this is concave down. If we said put about right here, that's all concave downward, right? Because it's just decreasing. So the next question that we could ask ourselves is, how do I determine this concavity algebraically? And so we're going to look at what we call inflection points. So the first thing it says, let f be the function that is continuous on an open interval, and let c be a number in this interval. If the graph of f has a tangent line at this point, so c, f of c, then this point is a point of inflection of the graph of f if, so here's where the important part of the definition is, okay? If the concavity of f changes from upward to downward or from downward to upward. So that instance in which your concavity changes from positive to negative or negative to positive or upward or downward or upward, when that happens, that value, that point is our inflection point. So to find that point of inflection, what you do is you take the second derivative, set it equal to 0, and find what c is. Or it could be where that function does not exist at x equals c. So keep that in mind. So it could be like there could be an asymptote or something involved that could change the concavity of our graph. The second derivative test, this is going to be if you just let your f be a function such that your derivative equals 0 and the second derivative of f exists on the open interval. We can determine if the value of c is going to be a max or a minimum using the second derivative. And so if the second derivative is positive, then we can say that it's a relative minima. And the reason is because if it's concave upward, well, that has to be a minimum. And then if it's less than 0 or negative, then we can say that it's going to be a relative maximum because it's going to be concave downward. And then if it equals 0, the test fails. And so that means that there's probably something else going on there, and so we're going to have to revert to using the first derivative test. So let's look at a few other examples. So this one here, it says find the points of inflection and discuss concavity of f if your function equals that. Well, probably the first thing that I can do to make it easier is I can distribute that through. Now I can take the derivative. So if I take the derivative, that's 3x squared minus 8x. And then if I take the second derivative, right, because it says points of inflection, so that means I need to think to myself second derivative. So if I take the second derivative, I'm going to get 6x minus 8. And so now what I can do is I can set that equal to 0. Add 8 to both sides. So 8 equals 6x, divide both sides by 6. 4/3 equals x. So this is the value of x in which I get the inflection point. Okay, if I plug the 4/3 back into the original, so if I plug the 4/3 back into the original, that's going to give me my inflection point. Now, just to save time, I'm not going to necessarily do that, but you would write, 4/3 and then whatever it is, what the 4/3 plugged in. So that is your inflection point. But the second part, it says discuss the concavity. So that means that on my number line, at 4/3, I now need to do the interval test, because this is where it was 0. And so on this side, let's just say if I test 0. So I want to plug 0 back into my second derivative test, or my second derivative, and I get a negative number. And if I plug in, let's just say 1, and if I plug in 1 into here, that means that I'm going to get, actually I want to plug in like 2. If I plug in 2, I'm going to get a value that's 12 minus 8, so that's positive. The reason why I can't plug in 1 is because 1 is not on that side of 4/3. So this is negative, this is positive, so I can say it's concave down from negative infinity to 4/3, and it's going to be concave up from 4/3 all the way to infinity. All right, next one. So it says, suppose that my derivative with -2 plugged in equals 0, And my second derivative with negative 2 plugged in is 7. What conclusions, if any, may be made about my function f of negative 2? So it only gives us information about the negative 2 for the derivative and where x is negative 2 for the second derivative. And so it wants us to wonder what's going on with our function with just that negative 2 plugged in. So going backwards, right, we talked about this here. We said that if my second derivative and I plug in a value and it's positive, it's going to be a relative minima. And if you plug it in and it's negative, it's going to be a relative maximum. Now on top of that, we said that if it's positive, my second derivative is positive, whatever the value is that we plug in, it's concave upward. Whatever it is that we plug in, if it's negative, so less than 0, it's concave downward. So we're going to use those to kind of help us here in determining this. So immediately, because I know that with my second derivative, when I plugged in negative 2, it gave me a positive value, I can immediately assume that it's going to be concave upward. Now, what that means then is that this value right here, because it's my derivative and it equals 0 when I plugged in that negative 2, well, that's going to be where, my slope is 0. So that means that this value here, if I relate it to this, it's going to become a minimum. So that means that negative 2 is a critical number because it equals 0. And on top of that, I know that then because this is concave up and that this is a critical number, that f of negative 2 must be a relative minimum. So let me rewind that just one more time. Because my second derivative is positive, concave upward, because this is a critical number, right, because it equals 0, that means that I can relate this to this. Well, since it's concave up, this has to be a minimum, and that's why I can conclude that f of negative 2 is a relative minimum. So it's a sketch graph of the function f having the given characteristics. All right, so we have f of 0 equals f of 2 equals 0. My derivative is greater than 0 when x is negative or less than 1. Okay, so we got to start drawing this out. So it's saying that at 0 and at 2, it's 0. So at 0, whoops. At 0 and at 2, it's going to be zeros. So I know it can cross there. Then the second piece, it says for, let's look at my first derivative, because that's what this is relating to. At my first derivative, my slope is positive when x is less than 1. So at 1, it's saying that it's positive here. At f prime x, it's a 0. So at 1, this is actually a 0. And then it's negative when x is greater than 1. Interesting. And then my f double prime x, okay. So that means that on this interval, it's saying everything is concave downward, right? So my second derivative, my concavity is less than 0, so everything is concave downward. Well, it doesn't really tell me anything about the y value, so I do have some sort of arbitrary y value here. I know that at 1, right, that's where it changes slope because my first derivative is 0, but it doesn't tell me how high or how low that is. I just know that it's concave downward, so I know it has to be above my zeros. And so something like that. I mean, if you drew it up here and then you drew the slope down, that's okay there. But let's kind of run through this again. So the first crosses at 0 and 2. Boom. My slope is positive when it's less than 1. So my slope, or it's increasing when it's less than 1. At 1, my slope is 0. It's decreasing greater than 1. So greater than 1, it's decreasing. And it's concave down. It's concave down. There you go. I sketched, what it could represent. To conclude this lesson, what is concavity? So what we're going to be looking at is the first derivative, and we're looking at how our slope is increasing or decreasing. So if the slope is increasing on an interval, we're going to say that it's concave upward. If it's decreasing on an interval, it's going to be concave downward. Then it says, what are inflection points? Inflection points are the value or the point on your graph, right? We first look for the x, but it's going to be the point on the graph in which your concavity changes from positive to negative, or negative to positive, or concave up, concave down, or concave down, concave up. Can I use the second derivative test to measure intervals on increasing and decreasing? The answer is yes, because the second derivative test is going to allow us to, it tells you itself, is my slope increasing or decreasing on that interval? So that's what we use the second derivative test for. So this does conclude our lesson. If you have any other questions, please leave them in the comments.